last time we saw some architecture. This time we're going to just to overview the 4 different ways we can synchronize the software to the hardware. And we're going to look at blind, busy wait, interrupts, and DMA. The reason why we have to synchronize has to do with a mismatch in speed. If you're running at 80 megahertz, how many instructions per second can I execute? We saw that last time. A RISC instruction executes how fast? 1 or 2 bus cycles, right? So if I'm executing an instruction every 25 nanoseconds, the software, by and large, is executing fairly quickly. Okay? Less than a microsecond, and I can do something interesting. But most physical devices, most input-output devices, have mass, have springs, have humans involved. And so they tend to be much slower than nanoseconds. They either run in the hertz range, like we played this game in 319K. How fast can you push the button? How many times per second can you touch a switch? Any gamers out there? Yeah, don't raise your hand. I don't need to know. But if you're a gamer, you're thinking, I can do 20 times per second. I can kill a lot of bad guys. 20 seconds, right? 20 bad guys are dead in a second, per second. But if I'm pushing a button 20 times per second, that's 50 milliseconds, right? And 50 milliseconds is a big number compared to 25 nanoseconds. So I have this mismatch. Now, there are some I/O devices that can run pretty fast when we're streaming data off a network card. Stuff comes off the Ethernet pretty quick. When I'm streaming data into a graphics engine or into the graphics monitor, that data can go pretty fast. If I'm streaming data between 2 computers, I'll stream it pretty fast. But by and large, most of our I/O devices are much slower than our software. The second reason that we have to synchronize has to do with the most important thing about real time is responding to an event. And we classified the events for which we have to respond to in either periodic events, sampling the ADD converter, outputting to the DAC, running our control loop. Those are periodic events where we must execute the software every delta t time. Okay? And others are aperiodic, where an input represents an event which I must respond to, or the output device is idle, I got to do something. So these are all things I have to respond to immediately, and so this is where synchronization will come in. All right. If we looked at an input device, we could see it has typically 2 states. Either the button is not pushed or the button is pushed. Okay, it's either busy or done. The output device is either busy or done. It's either working or sitting there doing nothing. And these are the states around which I want to synchronize. And it turns out in both cases, this busy to done state transition here, okay, this busy to done state transition is the event with which I am going to trigger an interrupt, make a gadfly loop go through. This is the event which classifies the beginning of my latency, right? Because we defined that last time, that the event must enter a response. And this is the response of the software. So if I touch a key, the keyboard goes from busy to done. The software has to respond to that key. If the printer is idle, if the output device is idle, I have to give it more data. And so if we look at this sort of state graph, this is the event, the busy to done, and the done to busy is the software response. So it's around this flow chart that we're going to talk about our synchronization. And we can see it in time. If you look at for an input device, if we looked in time, we can see, we can classify the input device being busy. That means there's no input. It's trying to figure out what's next. And then that input becomes available. That's the busy to done state transition. The software will recognize this state transition, read and process that, telling it to give me another one. And illustrated here on the bottom are the 3 of the 4 ways that I could synchronize. I could just wait and tell you to type at exactly 3 characters per second and just read the keyboard 3 times a second. That's kind of stupid. But it is appropriate when the time to do the input or output is fixed and known. I can actually do this, and small. So if it's fixed, known, and small, then it's appropriate to use a blind. If the time to do input output is fixed, it is small, and is known. Now, for example, your A to D converter, it takes 9 seconds to convert. 9 microseconds to convert. That's an example where you could have used blind. If we poll a status bit, that's called gadfly or busy wait. And the one we're going to do in this class is interrupt. We'll have this busy to done state transition, set the trigger flag, causing the interrupt. And then the service in that interrupt will perform. And this can be real time. Why? How is an interrupt a real time solution to an input system? Because I can have bounded latency. Okay? So again, what's the latency of an input? Time between when the time between when it goes from busy to done till the time I read the data. Right? You see that from this time to that time. And an interrupt allows me to theorize, to make it a high priority interrupt, and boom, I'm there and within microseconds. Right? All the time, 100% of the time. Assuming this is a high priority interrupt. And assuming your lab partner doesn't disable the I bit, which we won't let them do that. Similar problem with an output. Again, if the output is doing nothing, it's idle, sitting there doing nothing, and when it goes to when we give it something to do, when the software writes data to that output device, it goes into the busy state where it's doing its output. And again, this busy to done state transition right here is the trigger, is the event, is the beginning of the latency that matters for a real-time system. If you're trying to write to a CD, write to an optical disk, the disk is spinning, the write head is active, and the disk says, I got a spot, what do you want me to put there? And you have a certain amount of time to tell it what to put there, or that disk becomes a coaster. And again, we're 3 ways, or 4 ways, but 3 ways shown here. If this time to produce the output is fixed, short, and known, we could use a blind. If we only have one output device in the whole system, and we don't care about real time, you could use busy wait. Or if you're taking this class, we're going to use interrupts, because that allows me to create a real-time system. Just like with the input, my favorite data structure is the FIFO, because it allows me to do buffered I/O. Buffered I/O is a fancy name to say we're going to run in background. We're going to run in the background here, and we're going to pass data into the background through a buffer. In this case, going to be the first in, first out, order preserving FIFO. Questions? Yeah.
Are we allowed global variables in this class?
Okay. The question is, are we allowed global variables? I'm going to go, you can't do this class without global variables. Okay, so the question was, what good is a global variable? Okay. And you've been taught they're bad, but global variables are required in this context of this class when we have multiple threads. Okay, we'll see that this is called a thread because it's executing in the main program. This is a thread. It's executing in the background, triggered by an interrupt. And to pass data from one to the other, I must use a global. Because as you know, when the interrupt happens, what happens to the stack? Everything is balanced. Okay, it gets pushed. You essentially, even though there's one stack pointer, until you get to 445M, there's one stack pointer, they're logically separate stacks. So the local variables in the main program are not shared or connected to in any way the local variables in the interrupt service routine. So whenever we share information between multiple threads, we must use globals. Now I will say the right way to do it is a private global. a global which is private to this FIFO routine, and then provide some public functions like put FIFO, get FIFO, initialize FIFO, that the other programs use to get at those globals. And that way your access to the globals is done in an appropriate way. We're going to do globals in this class. One other place that we don't have to do it but I love to use globals, and that's in our debugging. In your Kyle debugger, there's a window called Watch. What's that?
Where you can look at the values of variables.
You can put variables in your Watch window, okay? And then you could set it up to periodic update, and you can look at your variables as your program's running. Now, it's a little bit intrusive because it has to go fetch that out of RAM, but we saw it sneaks in the backside, by the way. Doesn't go through the system bus. Sneaks in the backside to get it out of RAM, so it slows it down just a little bit. But we'll use global variables during the debugging phase. Like I like to count the number of interrupts. I'll just add a global variable that says, how many interrupts I have. So when it crashes, I can look at that global variable. Because after a hard fault, the global variables are still there. So you can look at what your global variables are at the time of a hard fault to see how many interrupts it had before it crashed. Did I answer your question? Yeah, globals. We want to, for good design, you were taught to use locals. Why? Just to not forget what you learned in the previous class. Why did we use locals? Locals are better than globals for situations that aren't those other two.
Security reasons.
Yeah, whenever we want to, the answer was security. Whenever we have something complicated, we're going to survive the complication by adopting a need-to-know basis. Okay? Just because I have a secret clearance with the government, I can't see every secret document on the planet. I can only see the ones that my supervisor deems that appropriate for me to see. Okay? I need to know. It reduces the complexity by hiding information or allowing information to be only accessible by those that need to know. And so that's the word scope. And to make it simple, we reduce the scope as much as possible. So local variables are still good, and you can see them in the debugger. There's a local variable window, but the optimizing compiler is going to make it very hard for you to see it because it's going to try to throw it away immediately. So it's going to be harder to debug the locals with the debugger. That's a good question. Any other questions? All right, let's go. All right, so when do we use busy wait? You remember from a flowchart standpoint, we look at the status bit, and if the I/O device is busy, we will wait, and if the I/O device is done or ready, we will then do the I/O. That's what it is, and we're going to use it when we have one or two I/O devices. We don't care about real time. We got nothing else to do anyway. This is actually this will be faster than interrupts if we just have one thing to do. On the other hand, we love our interrupts, and we use interrupts not because they're fun. I'll make you use interrupts on the test, not because it's the right thing to do, but because I want to make sure you know how to do it. And so this semester, interrupts are fun, so we'll use interrupts everywhere, just so you learn how to do it. And then when you go out and become practicing engineers, you can decide which one is most appropriate. So examples are, if I can't predict when data will come in, like answering the phone, that's a good one. When should you pick the phone up? Twice, every 5 seconds, pick the phone up. Okay, that's what Mom's doing, by the way. Call her this afternoon. She's looking at that phone. She's doing busy wait on the phone, by the way. I know my mom does. You know how you can tell? You know how you can tell? Yeah, I answers on the first ring. Well, the rest of us, just have to wait till that phone goes off and we pick it up, because we don't know when it's coming in. When we have lots of devices, and some are fast, some are slow, it's easy to mix multiple devices together using interrupts. So we just let each one interrupt when it needs to perform its service, and that's a way to mix a lot of devices together. If the load varies, in other words, what happens at lunchtime at Wendy's? You get a queue, right? You get a queue. And we saw the FIFO. So the FIFO allows you to deal with variable loads. And so we'll buffer the I/O process, and so that when the times are really busy, we don't lose our stuff. We don't lose it, we just buffer it. And so we'll use the FIFO queue nature to solve problems with the variable load. The opposite of only having one thing to do is having lots of things to do. And alarms is a good place to use interrupts. For example, if you've got a smoke detector, how often does the fire happen? Not very frequently, but when it does happen, it's important, and so we'll deal with an important but infrequent. You have a hard fault, by the way. Anybody got hard faults yet? Yeah, hard faults. That's actually an interrupt. It's a hard fault interrupt. It says you just access something that doesn't exist, because remember, most of that address space doesn't have anything. So if you access one of those empty spots, you'll get a hard fault. I remember when the first, I showed you a picture of that IBM PC. It had a wonderful feature, and that is if you divided, this was the original 1983 one, if you divide by 0, you got a blue screen. You got a unimplemented divide by 0 hardware fault. Stupid software. They fixed that for you. Yeah, Pat likes. As you know, I think highly of him. He had an interesting observation. Is what do you do with a computer that can't read and write memory? If your memory fails, okay, what can you do? You're a computer. You're an embedded system, and your memory has now just failed. What do you mean? I'm an embedded system. There's the wall, and my memory fails.
Down some more, he starts.
I can't read. And my memory has failed. There's nothing you can do. You can't execute opcodes without memory. You're stuck. You're dead. Okay. So there are some things. Now, if you have two memories, you can use the backup one, I guess. If you got two processors, you can use the backup processor. You run three processors in parallel and use voting. But when you lose memory, okay, you're in a situation that's very catastrophic and bad.
Just backup processors, or
No, it's just people just die. He said the question was, in a pacemaker, what happens if the memory fails? You're dead. Which is why they use 1992 technology, because it's much more stable.
back when things were stable.
Yeah, well, 10 years later, it is stable, right? Technology today will be stable in 10 years. The new stuff is highly unstable, because they're all jumping over each other's back to be the fastest A to D converter, so sometimes we use old stuff just in critical situations to make it more reliable. Yeah, you know what your hard drive does, right? If you want a very, very protected hard drive, you've got information on the cloud. What do they do to make sure you don't lose the data? You should go buy one of these $10,000 disk drives. What are you going to get? If I want a very reliable memory, and I've already actually alluded to it, and I'm going to use multiple copies. Okay? I'm going to use multiple copies, and when one of them fails, it'll still run because two are still running. Okay? And then a light will come on, and they'll hard swap out that one that's broken before the other one breaks. Yeah, so reliability is a big thing, but you got to know if memory's bad. Somebody's got to tell you, right? Because you may want to shut down in a graceful way if you can execute anything. Power failure is a fun one. We'll get an interrupt when the power's going down. We can use some debuggers, not this one because it's JTAG, have used interrupts to use breakpoints or to use single stepping, and we're going to use them for clocks and both the A to D and D to A. Now let's do the fun one. This one will not be on the test, but it may show up in a job interview. And we saw that when we used busy wait when there was nothing else to do. We used interrupts when there's lots of things to do and we want it to be real time. We're going to use direct memory access when we want to go fast. Okay? Examples of fast are think about your graphics driver. Okay, so how many pixels high is this? How many pixels high is your screen? Okay, just round numbers. 1,000. Can I just do the math because I didn't bring my calculator? About 1,000 pixels high. With me?
770.
Okay, so how many pixels wide is it? Again.
800.
Yeah, 1,000. Can you guys are going to make me get out a calculator? I got about 1,000,000 pixels on my screen. About. Okay. How many colors are there? 3 colors. Yeah, there are only 3 colors on here, aren't there? Yeah. No, the gray, that's a color. Yeah, 250. You want to do 8-bit color? That's fine. You can do 8-bit color. 8 bits. All right? All right, fair enough. 8-bit color. So this is 10 bits. That's 10 bits. How many times per second is it refreshing?
60 to 120.
Yeah, 60. Okay, I'm going in bits now, right? So 6 bits, right? About 60. So how many bits per second is that? Bunch. Well, I guess can you 20, 34, right? That's how many bits per second are going from somewhere from the memory of my graphics controller onto the physical graphics for the device. Okay? That's a lot of bits. Okay? Now, it turns out not very many of them change, and so I might not have to do them all. But that's fast compared to my gamer guy pushing the button 20 times a second. Right? This is a lot of bits per second. And so we're going to want a way to go fast. Right? We're going to want a way to go we're going to want a way to go fast. And the way we're going to do it is we're going to take data. In this case, this is an input device. Okay? And I'm going to collect data from that input device, and I'm just going to stick it into memory. And I'm not going to execute any software. Now, it turns out in this particular architecture, it's going to take 2 bus cycles for this to happen. In one bus cycle, it's going to go here, and the second bus cycle is going to go there, but it can go continuous. Right? So on this particular processor, I can stream about 32 bits or 4 bytes every 25 nanoseconds. Okay? From an external device into memory, or vice versa, I can stream it from memory to an output device. And again, it's going to take 2 bus cycles. It has to come into the processor, and then it goes out. If this is intriguing to you, I've got some starter code for you to play with. Does anybody see my hat? I'll have to bring it in. My hat with the lights. It uses DMA because it's got very high bandwidth. But there are 4 example codes. The first one is transferring a block of memory to somewhere else in memory. It's got no I/O device. The second one is I'm streaming data out to the DAC, and then the other 2. This one is like a logic analyzer. I can stream data from a port right into RAM, and this one is the one I use for my hat, where I'm streaming data from RAM out to the device. Questions?
Can Isn't this the same thing as memory mapped I/O?
No, there's no software executing. Software, he said, is the same as memory mapped I/O. No, because if I were to stream data from memory, right, I'd have to do something like this: load R, R0, R1 plus, right, and then I'd have to do store R, R0, R2 plus, right? Oops, go back. So if I wanted to, and then I'd have to go loop. I have to go something like sub R3, R3, sub S, R3, R3, 1, branch not equal to loop. So if I'm trying to pass data using memory mapped I/O, I'd have a pointer to one spot in memory, I'd have a pointer to another spot in memory, and I'd either increment or decrement the pointers and have a counter. That is slow, right? Because if you count the number of instructions, I got 1, 2, 3, 4. The sub is 1 cycle, the branch not equals 3 cycles. So I got 1, 2, 3, 4, 5, 6, 7, 8 cycles to send 32 bits. That's 4 times slower than this. Because I don't have to execute instructions. I just go boom, 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 boom. Yeah.
So there must be like a DMA controller.
Oh yeah, he said, how does it happen? There's a D as a controller. And it turns out on many machines, programming the DMA controller is just as complicated as programming the processor. And ours isn't. Ours is pretty simple. You set up the source address, the destination address. Do you want to increment either, or do you want to decrement either, and how many bytes you want to do, and what do you want to do when it's over? It's pretty straightforward. Some starter code if you want to play with it. It's awesome. But we're going to use it to go fast. Okay? So an interrupt is what we're going to start to do next time, and that is a automatic transfer. And we have to be able to determine who it is. We've got to determine the source. We've got to be able to acknowledge. And so it's all about the trigger. So we'll see the trigger is the most important thing. All right, so what we just saw in this lecture are 4 different ways to interrupt. Which one's fastest? Fastest one is DMA. Which one do I use for real-time systems? Interrupts. Okay, so that's the basic of what we should have got. And we're going to talk about the details of interrupts on Friday, and we will see you on Friday.